So I'll be talking about my activities with respect to learning, and in particular, how that can impact the natural economy. And so the first start with the concept of data. I'm going to argue first that there is a lot of overlap or similarities between humanities objectives that we are reaching. So the energy, of course, fits energy and entropy, and energy stands for placement of work, energy, human labor alone. And then the entropy stuff is part of intelligence for application. And industrial revolution, I think, how we're in the middle. Now, this person will know, speak well, that the revolution, the information revolution, is a revolution of free energy. Well, but of another kind, intellectual energy. And so this is where that lesson, free energy is machinery. And I will make this concept of free energy has actually created a lot of so these are actually the results of thinking about the energy the context of the generation. The repetition is probably the delta in flavors. Why? And so this is getting so good that all right. Machine, there's a bit of hard competition, long with competition. Painting that caption there, AI generated one of our competition, artists on caption because they first thought of pictures amount of copyright, deal out of data from but the most recent state of the art in this video generation, video context. Then here. And you can sort of fantasize with the show. Right? This is like it could be here. The video, the short videos, give it another few years. You'll get the entire game, the entire maintenance based on the script, and then of course you have the script out of that. Now, what I'm interested in small. I'm interested in science. In other words, if science is a powerful tool, you can collect your data on this first alcohol, this is so people after that you need to apply in order to keep it inside of this reactor without touching these sort of the boundaries. And this one is some of our own work, some of the earlier versions of molecule generation methods. So here you would say I want a molecule with these kinds of properties, and then it would generate candidate molecules with these kinds of properties in your computer. Of course, they might still have issues. They might actually not precisely have the properties that you wish, and so you would then have to go through further simulations and actual experiments to verify whether that candidate is a good candidate. In fact, I'll argue we'll need to further optimize. This could just be initial step for a further optimization. Okay, so now some equations. So I want to argue that, in fact, there is a very deep correspondence between physics with latent variables and sort of free energies in physics. So here on this side, I write down, or maybe I should, for a physicist, I should start on this side, because you're all familiar with this. So this is the free energy of a system in equilibrium, which is equal to minus t, the log partition function. And you can upper bound that by a variation of free energy, which is perhaps the most natural way in which you can assign a free energy to a non-equilibrium system. And that's given by the expected Hamiltonian under that distribution Q minus the temperature times the entropy of that Q. And this always upper bounds this. And there's actually quantum versions of this as well, I believe. And of course, P is the equilibrium distribution defined by the Hamiltonian and the temperature. Now, if we go to this side, in machine learning, we write down precisely the same equation, but here we write down the minus log probability over our data X. We call this the marginal likelihood, where we have integrated out all the latent variables. So think of latent variables as microscopic degrees of freedom that we are not interested in and that we integrate out, but that give much more expressivity to our models. So minus the log probability is upper bounded by an energy term, which is the log probability jointly over X and Z. So I would invite you to think of X as microscopic variables like temperature and pressure and things like, you would have in thermodynamics, and Z as the microscopic degrees of freedom. And so we could have written this as F of temperature, and I would write log of P of X, the observables. And so that's the entropy term. Again, the expected value over a probability distribution, in this case, Z given X, the posterior distribution over the latent variables given the observations, or the microscopic degrees of freedom given the observations, minus the entropy of that distribution. And so these things not only look very similar, but I'm going to argue they are the same. And so in some sense, I want to argue that in machine learning, we study physical systems to some degree. They're typically out of equilibrium, but sometimes in equilibrium. Okay, so let's look at, for instance, a famous algorithm in machine learning, which is called the expectation maximization algorithm. So what does that do? There's an E step in which we update this variational distribution Q to minimize this bound. So you can think of that as a physical system that's relaxing into its equilibrium distribution. And in the physics, that would mean that if you keep the Hamiltonian fixed, but you minimize over Q, it means that that's a definition of heat. So how much heat do you generate if you keep the Hamiltonian fixed and you then opt to minimize over the distribution rho over Q of the sort of latent variables or the microscopic degrees of freedom. And then there's the M step, which is you update your Px of Z as your model of the data to minimize the bound. You minimize the same bound. And that you can think of as performing work, which is you now change H, you make the Hamiltonian a function of time. And if you change H, so keep Q the same, that's actually the definition of performing work on your system. So here we see something interesting, which is that the typical algorithm that's used in statistics and machine learning is actually alternating, generating heat and then generating work, or doing work and then generating heat again. And I want to point out that there is somebody who has analyzed this very deeply, which is E.T. James. So E.T. James was actually a physicist, but he did a lot of really important work in statistics. And a lot of his work is also used in machine learning. And in particular, he invented the maximum entropy principle, and also the maximum caliber principle. And basically what he says is that really you should think of statistical mechanics in a Bayesian way. You should think of it as that the entropy is not some physical thing. It is actually our degree of ignorance about the microscopic degrees of freedom of the system. And if you read literature, there's many physicists who agree with him. I don't think, it doesn't have to be controversial at all. But it is interesting that when we think about distributions in AI and machine learning, we always think that is the ignorance we have about the system. That probability reflects our ignorance about the degrees of freedom that we can't see or observe. I think the same is true in physics. Okay, so now, why is it interesting to apply machine learning to the sciences? So the first fascinating thing I find is that, of course, physics, or I should say science, spans an enormous range of spatial temporal scale, right, from femtoseconds and picometers to all the way up to giga years and light years, all the way from particle physics to astronomy. But many times the techniques that are being used are quite similar, right? It's typically an ODE or PDE that we write in, or stochastic PDE, so they're often very similar. I'll argue more. And so this means that if we can get our machine learning methods to help with those methods, we can sort of impact all of these scales. And that's actually currently happening. I'm personally most interested in this place, the molecules which sit nicely on the interface of quantum and classical. We treat the ions classically and the electrons quantum mechanically. And so we need a bit of both. And of course, as you all know, almost everything is made of molecules of some kind or other. Either, except for, of course, the four fundamental forces, which are not made of molecules. And also when we smash them very hard and we make them into plasmas, or, if we rip them apart in collisions, of course, then they're no longer molecules, but basically at our temperatures and scales, everything you can touch is basically built of molecules. And the application areas are very exciting, I feel. If you can, control or accelerate simulation of molecules, let's say small little molecules that attach to proteins, then you can accelerate the field of drug discovery. Of course, molecules are at the core of photovoltaics, solar cells, lubricants. I've heard that 20% of all the energy that we waste is basically due to friction. So if you build better lubricants, you can also cut that down. Catalyst design, in which you can accelerate chemical reactions. For instance, if you want to sort of create hydrogen out of water by splitting it, or if you want to create sort of synthetic fuels out of carbon dioxide and water, or nitrogen fixation. Anyway, there's many applications that depend on understanding molecules better, and I think here is where machine learning can make a very large contribution. Now, what is changing in this field? So why is machine learning making an impact in this field? This is something that's happening right now. And there's many, and if you talk to a high energy physicist, will probably give a different answer where machine learning is making an impact. I'm going to focus on molecules. And the important thing is that what's happening, the first thing that's happening is that we are moving from actual physical experiments, of course, which we will always need physical experiments, but increasingly we can reduce the number of physical experiments we do in a test tube into sort of digital simulation. So in other words, we can now simulate collections of molecules with maybe millions or hundreds of millions of atoms using molecular dynamic simulations, using something that's called a force field, which is a machine learning method that it can accelerate the computation of the forces which you need to do the simulation. Now, the second advance is what we call amortization. And that's when we go from simulation to emulation. And so I've sort of illustrated that here with this example. So let's say you're an auto manufacturer and you built your first car, and you're going to test that car, either in a physical wind tunnel, or you're going to do this in a digital wind tunnel. Anyway, you're spending a lot of money on trying to compute the properties of that particular car.
Okay, so then the usual paradigm is you go for you design your next car and you go again through this entire process again, once again. That's expensive. Now, what the sort of the amortization step is that instead of throwing away the data from your first experiment, let's say your digital data or your experiments, you store them in a database, and then you train a neural network that can predict the outcome of this simulation. Of course, you would also need some kind of assessment of how reliable that particular simulation is. But if you have that, then in fact, you can skip this expensive step. As you get better and better at this emulator, you can then start to skip this expensive step. And that's what we're seeing in molecular dynamics simulation is these force fields. Instead of doing a full quantum mechanical DFT calculation, you can now use the neural network, and it will predict the outcome of the DFT calculation. Now, the techniques that machine learning is developing with physicists and chemists in this field basically span all the scales of molecular simulation, all the way from ab initio electronic structure methods, for instance, neural quantum Monte Carlo methods, to DFT, where the functionals of the DFT are being learned from data. I will say a little bit more about that later. Actually, I'll do it on the classical version of that. Then there's these force field methods, which I just mentioned, which you need for MD simulations. And then you can go up to particle-based methods and force-grained particle-based methods, which you can all sort of shortcut by machine learning methods. And then at the top of that, there is classical DFT functionals. I will say a little bit more detail later. And then finally, at the top is basically full continuum methods. In particular, weather prediction is a great example of this. I've seen weather prediction going from meteorologists saying this will never impact what we do because if we do numerical simulations, we've been developing this for hundreds of years, machine learning will not replace it, to in a few short years, sort of almost panic, like, okay, this is actually working so well, we should get into this very, very quickly. Now, of course, the story is slightly more complicated in the sense that if you get new weather patterns you've never seen before, these methods might not be reliable. And so it's not always the case that it does better, but the acceleration factor is sometimes 4 orders of magnitude, right? So that's huge. Okay, so here in a bit more detail, maybe the equations that we replace or improve with machine learning methods. So this is obviously the time-dependent Schrödinger equation, and this is a beautiful visualization, I guess, from Quantum magazine on the electron structure that is sort of fluctuating under the Schrödinger equation. And as I mentioned, there's 2 methods which accelerate this. One is the DFT ML functionals, and the other one is the things like Fermi-net and Pauli-net, which are more like quantum variation Monte Carlo methods. And then at the level of the molecules, we have the Langevin equation. And here we have the force fields which accelerate this, which replace this term here. And then at the level of the Navier-Stokes equation, we have what we call PDE surrogates, which in fact, they don't even try to simulate that thing anymore. They just take the input state, the full state of the weather globally, and predict the future weather states, full globally weather states. And they are now getting very good and the reason why they get so good is that there's a lot of data available in this field. So the meteorologists have been very good at storing all their data. There's petabytes of data available, and these methods get very good. And this is
can you quantify how much better they've gotten than previously with other methods, or where they stand on the accuracy?
Yeah, so the latest sort of evaluation is saying that they're about equally good or slightly better than the numerical simulators if you evaluate them on some somewhat standard weather patterns and 10,000 times faster. So I think the reason why meteorologists are so excited is that they seem to actually are at least equally good in terms of prediction accuracy. Again, I want to add the asterisks that, of course, in numerical simulator, you can, for instance, if you do prediction of climate change, right? So I would trust an actual numerical simulator more for the reason that by construction, since the climate is changing, it will, it will have to predict in situations that it has never seen before. And then it's unclear how you can rely on this input. So there's a big step on verification and reliability that still needs to be made. So the last is basically what's called classical DFT. It's also a continuum method. It's this particular PDE that we are trying to solve. I'll say about that more later. Okay, so maybe so plotted out quite slightly differently, sliced it in slightly different way. So we have equilibrium methods, and if we go like this, we go up in scale. So we start with quantum DFT, MCMC, and MCMC, which is where we use machine learning. Boltzmann generators, which are machine learning methods that generate data from the equilibrium distribution. And then this is classical DFT, which is just thermodynamics version of trying to compute the density profile of a particular liquid in a external potential. And then, of course, what's interesting, I find, is that these two DFT methods are almost the same method, even though they operate on very, very different scales. Of course, this has to do with anti-symmetry of wave functions, and this one doesn't have to deal with that. But otherwise, these methods are, the mathematics of it is very similar. And then in non-equilibrium methods, we have the Schrödinger equation here, the time-dependent Schrödinger equation, molecular dynamics with force fields, and here you could say dissipated particle dynamics and conditional sampling. At this scale, you go up further is hydrodynamics, of course, also non-equilibrium. And that's interesting that these two methods are again quite similar because you can actually write down a Schrödinger equation almost as a sort of hydrodynamics equation. And that's also very interesting. Okay, and I should mention that, of course, the top part has always been continuous methods and the bottom part were discrete particle methods. Okay, so probably not necessary in this audience, but a molecule, in order to simulate a molecule, you can treat the atoms or the ions as classical objects. We just look at their position, and we have a velocity to compute in order to compute how all of these things change. That's, of course, just Newtonian mechanics, very simple, hundreds of years old. The problem is if you need to compute this force here, this force is actually mostly determined by the electronic structure of this thing, and that requires you to solve the Schrödinger equation, particularly the time-independent Schrödinger equation, which you need to find the ground state from which you can then actually compute the forces. Right. Okay. So one of the things I've been busy with over the last years is to include symmetries into neural network predictors. So if you build, let's say, a force field model out of a neural network, you can ask yourself, okay, how does this neural network, how is that going to understand the fact that there is natural symmetries in these models that it should respect? And this is to just explain to a different audience precisely why symmetries are so important. Of course, Maxwell equations have this nice symmetry that electricity and magnetism are changed into each other by moving the frame of the observer. And here we could argue that general relativity has a symmetry between acceleration and gravity. And of course, we also know that the standard model is organized in terms of symmetry groups, which map particles into each other by group transformations. So how does that play out in a neural net? So if I build a neural net, I want the following property. I want that if I take an input image or an input molecule, and I transform the molecule, so let's say in this case, I translate the image or the image itself. Then what I want is that if I first translate and then filter, so this is a neural network layer operation that sort of processes the input into filtered input. If I first transform and then filter, that should be the same as first filtering and then transforming. If I close this diagram, if I did like this, if my neural network has this property, then I can guarantee that the neural network respects the symmetry, which means if I rotate, let's say, the input molecule, then whatever vectorial quantities I have will rotate nicely with it, or whenever tensorial, or if I have a scalar property, it will just remain invariant. Now, there's important advantages, in particular, data efficiency is really important for these models, but also the models generally get better. If you want to read about this, by the way, this is a great thesis that's about to come out by Maurice Weiler. It's 500 pages, it's richly illustrated. These are images, from his thesis, and it's a really good introduction in this field, and it's quite mathematical the deeper you get into it. Okay, so in order to actually simulate molecules, what we will need is a neural network structure that looks like a molecule, at least. That is a natural fit to a molecule. And a molecule you can think of as a graph, where you have the atoms and you have these sort of interacting atoms. They form a graph. And then we want some kind of update on this graph that takes an input. The input could be the positions of the atoms, as well as the sort of the type of the atom that we have here, and possibly other features if you have them. And it then updates iteratively, and in the end, it needs to predict something, like it wants to predict, let's say, the energy of the molecule or something like that, or the forces. And so we do this by these, these updates, these message passing updates, where we first compute a message between node I and J. That can depend on the states at node I and node J, which are these H's, which change. And it could, for instance, depend on the distance between these atoms. And then I also compute a velocity field. Okay, let's skip that for a moment. Now we aggregate the messages that go to node I. So we take all these red messages and we aggregate them by summing them or some other permutation invariant operation. And then the last step is that we update H by taking the aggregated messages and the state at H to another nonlinear neural network to create the new H. And we iterate this process many times, and that defines a neural network. It's called a graph neural network that you can then use to compute forces, let's say, and other properties of molecules. Now, of course, the important step was to make these graph neural networks equivariant, so to make them understand the symmetries of the problem. So that's what happens here. So let's say you start with a graph. It has positions and scalar properties, but also vectorial properties like velocities. And I want that if I process the graph and then transform it, like rotate it, I want that the same as I first rotate and then process. And so we've designed algorithms basically that do these things on a graph so that they respect the symmetries. And so this led to these particular models called sort of steerable force field models. So the first one is called SE3 transformer. In fact, this model was used by one of the labs on protein folding. I think it was Rosetta Fold by Baker's lab has used this particular model to do their successful work on protein folding. Turns out that AlphaFold also uses something which carries the same name, but apparently they developed their own version of it, and so it's a sort of, I guess, co-developed. So these are representations of spherical harmonics, which are the steerable or irreducible representations of the rotation group. And here you see these representations or these steerable or sort of these harmonics visualized in a particular way as they change through, pushing the information through the layers of the neural net, right? And here you see this closing of this diagram. So basically, this means that if I rotate the molecule, it will completely understand that nothing has changed about the problem. It's just it's just a rotated version of the input. Now, this is not trivial. I want to say it feels trivial if you look at it this way, but of course the numbers you give it to the input, they change if you rotate something, right? You really have to tell it that if you rotate something, that's actually the same thing, but a rotated version of it. Yeah. Okay, so now the next topic is generative AI. So this is the technology that produces all these beautiful images that I showed and videos. I think this started somewhat in 2015. Where this paper was written by these Stanford folks and Berkeley folks called Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. And so this emphasizes the point I wanted to make in the beginning, that there is a very deep connection between machine learning and statistical physics, in particular, non-equilibrium thermodynamics, right? So they literally used the language of non-equilibrium thermodynamics to come up with this algorithm. Now, this algorithm is now based on, is not the basis for all these really good algorithms. I should say it is a development of this, but this was the first one. And the idea is that you start with sort of a data distribution, which is a highly structured manifold. Let's say it's very low entropy. And then you just apply the second law of thermodynamics to it, and you just increase the entropy using some diffusion process, right? And then as that happens, you'll learn the algorithm to run against the second law. So in other words, you learn it to so pick a point here and just undo this path back to the structured manifold. Right? So it's very unnatural for a physicist, but this is like running backward in time, literally. So you run the movie backward in time, and you learn how to run this movie backward in time. So to make this really practical, this 2021 paper came in, and they formulated it as a stochastic differential equation, like simply a Fokker-Planck equation, Brownian motion. This is just Brownian motion version of that. And then the inverse, the time inverse version of that picks up this extra term, which is called the score function. It's the gradient of the log probability of the input data. And now you train a neural network to, to simulate or to whatever, to approximate this term. And you can do this very efficiently, which is what these people showed, by actually picking at random a data point and then picking at random a level in your neural network, and then doing an update at that level, and then picking another data point at another level, and again doing that update. So this made this highly practical. And we took this idea and said, okay, can you use that to generate molecules, right? So, you can think of this as an image of a dog, and then this is the second law of thermodynamics. It turns this molecule into a blob, an unstructured blob of atoms of random types. And so the only thing is now that you need to learn to undo that. You generate things of these random blobs, and you turn them into actual thermodynamically stable molecules trained on a data set. And of course, we want to make this whole thing equivariant, meaning it needs to understand that the probability of generating something here or here or here or rotated must be mathematically equal. There shouldn't be a difference in probability. And so if you then, unfortunately, somehow it's a bit doesn't go very smooth, but you can sort of get the picture. This is if you actually track the algorithm as it is running against the second law of thermodynamics and turning a random blob into a structured object, you can sort of see how that sort of operates here. You see both the color changes, which means the type is being determined of the atom, as well as the position is being changed. And the bonds are basically by looking at the distance between these things. No. No. Right. Okay. Yeah. So I already mentioned this. There is an, oh. Okay. I guess we're getting stuck somehow. Okay, it's very much delayed. Let's see what happens. But so this is some of the work that has happened over the past 2-3 years on modeling weather prediction. So one of the first ones was actually developed here at Caltech, which is ForecastNet by that group there. Andrew's in the room. I think you were on this paper, right? No. Oh no, on this one. Okay, follow-up papers. But it's probably an NVIDIA paper then, right? So so this ForecastNet, the Anima is on this paper, I'm sure. Anyway, it's too small. And so later this paper came, Pangu weather. This is still one of the state of the art, and this is GraphCastNet, which is a model by DeepMind, and many papers came after that. And so this is now, these models are as accurate as weather prediction if the weather isn't too crazy. And 10,000 times faster. Okay, So I'm now going to run through a few applications in the remaining time in which I've been involved. There's one I will treat in a little bit more detail. For instance, where this is starting to make a huge impact, like in weather prediction, there's this other application area, which is a drug design and drug development. So you have a pocket, which is these green nodes, and that's the pocket of a protein, and you're trying to fit a particular molecule in there that could sort of neutralize that particular protein, let's say as a drug. And so the version of this generative modeling is now you keep these nodes fixed, but then you sort of diffuse or anti-diffuse or denoise these particular positions of this drug-like molecule into this pocket, and then hope that that's a good drug. And so here you see again a movie of that happening. And these are the, and you can also work with anchors, so you can say, I want these parts of a molecule sitting in these places because I already know that's a really good fit, and I'll complete the molecule for me for an arbitrary number of anchors. Okay, here's another problem in chemistry, which is called transition path sampling. This is the Sisyphus project. So Sisyphus was this poor guy who would have to roll up this rock on a hill, and then by the time he was there, it would roll back down, and he would have to start all over again forever, right? So that was his the issue that he had to deal with. And so, but it is almost the same as the issue that a molecule has to deal with. If it's sitting in some metastable state and it wants to move to another metastable state, it has to go over this energy barrier here, or in this particular case, a free energy barrier, because we have integrated out a whole lot of dimensions. And so if you just do molecular simulation, what will happen is you will wait forever, because it's very unlikely you will see the right fluctuations that will get you over that energy barrier. But there's a trick. What you can do is you can help Sisyphus a little bit by adding a force. And that's sort of, this is large band dynamics. This is the usual, the change in position is given by velocity, the change in velocity is given by the usual force, plus noise, plus this additional extra term, which only exists in your computer, not in real life. And now you're training up with the machine learning algorithm, you turn this into a neural net, and you train up this U such that the molecule is encouraged to take sort of the path of sort of the saddle point, the lowest peak in some sense. Now you can formulate this as what's called a optimal control problem, because you can just give the molecule rewards. You say, if you make it to the other end, you get a nice reward, but you pay a penalty for every time you have to do work. Every time you have to apply forces, I'm going to give you a penalty. And if you do that, you encourage the system to get over these energy barriers and sample into these other sort of metastable states. And here, there's a little simulation of that. This is already a bit old. It's already better now. So here's the molecule, and and this is the free energy surface. So here we move it along in this free energy surface. Here you see the molecule changing under the extra force that we're applying to it. And you can see here that the potential energy is going up. It's pushed up the hill, and then and it gets into this other metastable state right here. Now we've done this also for larger molecules, where this basically turns into some kind of folding problem, right? You're just trying to fold this thing now into a metastable state. Okay. Given time, I'll probably speed up a bit. Right. Okay, so the last sort of technical topic I want to discuss is classical DFT. This is something I've been working on more recently, together with this student here, Jacob Dijkman. So the problem that you want to solve is a classical fluid, let's say described by a Leonard-Jones potential. You write down the grand canonical potential function, and you split it into the internal free energy, which describes the liquid without any external potentials, and the interaction of the liquid with external potential. So you could think of this as a molecule that the liquid is interacting with, but also you could think of it as some kind of ball or something like this, a box. And then, of course, there's the chemical potential that manages the number of molecules in simulation. Okay, what the program is that we want to learn this function, this free energy function of the internal degrees of freedom from molecular dynamics data. Now, in the past, physicists have written down lots of equations for this F, right? Because there's a theory called okay, I forgot the name right now, but it's a theory that describes, you know, the physics behind, let's say, Lennard-Jones particles, and you can write down what the free energy approximations or the approximations to this free energy would be. Now we're going to take a different route. We're going to say, well, because we know what the microscopic degrees of freedom are for this problem, so we can just simulate MD data, and then we're going to learn what this function will look like. And once we have F, there is an actual procedure to then minimize this rho, you know, this omega over rho, by minimizing this full thing, in order to get the equilibrium distribution for any new potential V. And then I should mention that once you have F, you can compute the derivatives, you can compute the velocity fields, and then this is the equation. It's just a Fokker-Planck equation, which is sort of strange velocity term here. It's over damped. This is the equation that tells you how the liquid will go to equilibrium in the presence of some potential. So we have two algorithms. I can keep going for how long, John?
Talk to step 5.
Until 5? Okay. All right, I'll make it easy with some extra question time. Okay, so the first method that we will use here is we start with some, let's say, some data, which is the data from the MD simulation, and then our neural network computes the free energy. So that's a number that's coming out of this. It's the free energy. It tries to approximate the free energy of this density profile. And this molecular dynamics, this comes from a potential. So you actually do put a particular potential in the problem. So then you have that. You can do now auto differentiation to get DFT rho. That's like this here. And then you can match that with the actual DFT rho, which you see in the data. So here you stick in the rho of the MD simulation, you push it through your model, and then from your model, you compute this DFT rho. You can also compute DFT rho from this equation, which you know holds true. That will also give you, for a particular rho, DFT rho, and then you match the two. You match the computation through the neural network with this computation, and that will give you an update to train this neural network here. Okay, so that's the first method. Now, the disadvantage of this method is that you have to create a data set in 3 dimensions, as well as for different potentials. So the second method we use is much better, which is now the input data is given by this radial distribution function, GR. Of course, this only depends on 1 dimension, and it describes the density of the particles as you move away from an arbitrary point in your liquid. And now we can generate data for bulk, so for basically 0 potential. And so we start with an input density, we compute the free energy, we auto-differentiate, we get DFT rho, we auto-differentiate again, and we get the second derivative, d squared f d rho I d rho j. So we get this object, which is the 2-point correlation function. Now the 2-point correlation function is related to this radial distribution function. So you from this data, you can actually compute this object, which is the actual ground truth 2-point correlation function. And then again, you match this object to the object you computed using your neural net, and you iterate. That's really nice because the data only has to be in 1 dimension. You can average over directions and locations, but also you can only do it for v equals 0. So you only have to create data for 0 potential. And once you've done that, you can now do inference, which is you have your neural net. So you take some random input and some random potential that you're interested in, pushed through the neural network, out of diff, that gives you DFD rho here. That's what you have here. And then you run this equation. This is called the Picard equations. If you run this to convergence, which is you get rho, you get DFD rho using your neural net, you run this equation, you go back to rho, and you iterate this until the whole thing converges. That should give you the equilibrium distribution for rho. And note, you've never seen this V, but now you ask it to predict for an external V. And here's what you get. So here's the rho. The ground truth is given by this Monte Carlo estimate of the density. This is the potential that we give it to this particular example. And then the first method is the red method, and then the second method that I showed is this sort of cyan line. And then the mean field approximation, actually this is better than the mean field approximation, is given here. And so you can see that the actual, whenever the physicist wrote down, tried to write down what this free energy is by doing approximations, they would make very systematic, this method would make systematic errors. If you train it from data, it is far better. It outperforms that a lot. And we're working with two physicists, so it's not like we are imagining this or something, or we're in our ivory tower thinking we're doing great. The physicists actually who are working on this problem have acknowledged that this actually does do a lot better. And we can go to very extreme potentials that it has never seen before. In fact, this method, the second method, has not seen any potential, and it gets very accurate predictions for the densities. In fact, we can also predict the free energies directly, which is none of these other methods, even the machine learning methods, couldn't do. So first of all, it's more accurate, but also we can, using our neural network, remember, it just predicted the free energy directly. So we stick in the density, and it predicts the free energy directly. It's much more efficient in 3D, and it generalizes better to new V. So it understands if you give it new Vs, it doesn't get confused, not overfit on these Vs. And here you see the errors in the free energy. If we increase the density, the blue method is the method that hadn't seen any Vs at all. And it predicts the free energies very well. And so these others, so this is this fundamental measure theory. That's the theory that people use in order to compute these sort of approximations. Okay, so that was sort of a bit of a detailed sort of description of some of the projects. So I'm not gonna, have two more slides, sort of inspirational slides. I think there is we are in a very special time in some sense, which is that not only has, of course, the molecular sciences, like in biology and chemistry and physics, progressed a whole lot, deep understanding of things, including quantum level. I think what's special is that the modeling sciences, the computational sciences currently have also matured a lot. Computational science and supercomputers, machine learning, obviously, and AI. And then hopefully quantum computing in X years can also make a huge contribution in, for instance, generating better data for these models. And then, of course, there's the application areas which are, pooling on all of these methods. So in sustainability, for instance, carbon capture is a great example of how you're designing materials, MOFs for instance, the energy transition, for instance, hydrogen production, and health, drugs, vaccines, or drugs against sort of resistant bacteria, for instance. So you could imagine that we might enter a material on demand age, having gone through all of these ages. Actually, this morning I was at a talk where indeed somebody mentioned we are in the plastic age. Very interesting. But I'm hoping that in the future we can actually, design materials on demand with some kind of search engine. So this is the kind of search engine I envision, which I plan to build, which is there is a generative model. So the generative model, you give it a prompt, you say, I want a material with these properties, and you have a trained generator, like the ones I've shown you, to get you a first idea of possible candidates of molecules. Here, this is MOF structure with these properties. Now, I acknowledge that is never going to be perfect. It would be magic if we would have something like that. But it would be a great initial condition for this phase. Now, in this phase, we have a bunch of choices that we can engage. One is, of course, the experiment, and there's a lot of development in robotic labs. Also here at Caltech, I think people are thinking about this very hard. Another one is computational chemistry simulations. These are typically expensive, but certainly they give you very valuable information. And then finally, these emulators, which are trained neural networks, they go way, way faster, like the weather prediction, for instance, but are less accurate. And now here's an agent, sort of a reasoning agent sitting here that manages the assignment of computational resources to each of these things. So it says, okay, I first run a few of these things, right? And now for a subset of candidates, maybe do some computations here. And then I have a few candidates left, now throw them in an experiment and see what comes out. And then the data that's being generated by these two methods then help improve again all of these neural networks. So the way to think of that is as a search engine, the way in which we revolutionized search on the internet by algorithms. This could revolutionize search of materials. You just type what you want, this thing gets fired up in the back, and it will give you a whole bunch of promising materials that you can then sort of test. So to conclude, I think there's deep connections. I argued there's deep connections between AI and the natural sciences. I think a lot deeper than people realize, in particular at the level of free energy, for instance. I also think that machine learning could become a new hammer for scientists. You could think of it as a microscope of some sort, or a data analysis tool. And I'm particularly excited myself about the applications with societal impact, such as in health and sustainability, for instance, new drugs and materials. And that's the last slide, and I'll open the floor for questions then.
Well, we have time for questions for Max. Well, let me start. When we make predictions generalizing from data, is it important to have some heuristic control over prediction error, or should we just proceed heuristically and hope for the best?
You want guarantees, right?
Yeah.
Yeah, I know. You've done a lot of work in making sure things are, you have guaranteed error bars. Now, for machine learning, this is pretty hard. So if somebody can give me guarantees, I'm all for it. But there's a trade-off. So the more guarantees you want to have, the less predictive your model is going to be. I think there is that trade-off, because if you make things more and more complex and more chaotic and more complicated, coming up with a guarantee on performance is very hard. However, as a sort of a surrogate for that, like, let's say, meteorologists use for predicting the weather, it's a life or death. It's actually a life or death situation for them, right? Because if you predict something wrong, people might not move, and then you might have a storm, and that might kill people. So for them, it's very important. So what they do is they have ensembles. So in other words, they don't make one prediction, but they have a very intricate way of initializing multiple predictors, and they just track how these predictions sort of start to deviate. If they all agree, then the uncertainty is low. If they start to deviate, then you should maybe do a more expensive simulation, and your models start to fail. I can see that whenever you design a search engine, I think it's super important that we have that type of uncertainty quantification. I should also say, if you're interested in the engineering question, if I have a complete black box, I have no idea what's happening in this black box, but it will give you the right answer. You can say, I don't want that because I don't know what's going on in your black box. But it could still, if that delivers the new drug for some disease, and you can test whether it does, you might still want it. And so for some problems, verification is a lot more important than for others, or sort of guarantees is a lot more. If you're driving a self-driving car, or you administer a medicine or something, you really want certain guarantees, I guess, or flying an airplane or something like this. But if you want to predict the stock market, and your method happens to predict the stock market really well, and you're making a lot of money. I mean, who cares how you did it? You're just making a lot of money. So
Other questions?
Thank you for the nice talk. I wanted to ask, if you kind of gave the best example of molecules, if you solve one molecule, now say you want to couple two of them, is the problem as simple as the sum, or you should just start again from the beginning? Like, is it
Right.
a way to let?
but it depends a bit on what, so it turns out that we are starting to see that, for instance, force fields can be generalized across, multiple molecules. There's also, you can make it bigger and, and so I think for certain methods, they generalize quite well to changing the molecules or changing the number of molecules and things like this. So it depends a bit on what precisely you ask. If you build a model that, say, tries to predict the binding energy of something, and you have changed, something dramatically, you should not expect that method should still predict the binding energy. So typically, the closer you sit to the physics with your models, the better they generalize. The more completely data-driven your model is, the more you have to worry that if you go out of domain, it doesn't work anymore. But did you have a special problem in mind?
I was just thinking about, say, two physical systems, which of the parts are easy? If I put them together and interact, is it easier to train from the beginning, or is some advantage of training with different parts and then couple?
Yeah, I mean, I think that we have to maybe think more about like precise example, but certain properties may be predictable by just combining the parts. Other properties might actually crucially depend on the fact that they are now sort of in a bigger system. And you might not be able to predict these things. I think microscopically, I think you'd be fine. If you look at macroscopic quantities, you might have to worry that, for instance, these predictions depend on the size of your system, and you may have to take that into account. But I guess we have to go into more detail to discussion.
So the part about generating new molecules using AI, have there been good success stories where the outcome was surprising, in the sense it was unexpected by experts who are using traditional methods?
I don't really know, I have to say. So certainly the models that we have done, I don't think they were at the level that a chemist or pharmacist was excited about it, in the sense that they might not even have looked like real drug molecules. But I should say this field progresses very, very quickly, and certainly the pharmacists and the material scientists are very interested in what's happening in this field. I think recent papers in materials generation, for instance, MetterGen from Microsoft, people seem to be quite excited about the things that it generates. So it can generate millions of stable materials, which are not actually in the materials databases currently. Now, whether that's something that anybody will want to manufacture, I don't know. But I guess maybe not quite, as it would be my guess, but give it a few more years, and I think it will work.